Please go ahead.
Okay. Good morning, everyone. I want to share this paper titled "Counting a Stationary Crowd Using an Off-the-Shelf Wi-Fi." So this paper is published in Mobicis 2021. Here is the outline today. I will first introduce the motivation of this paper, and then I will give the mathematical model, the Wi-Fi processing pipelines, and finally, I will show the experimental results and give a conclusion. So here is the motivation for the sensing with ubiquitous Wi-Fi signals. Thanks to the Wi-Fi signal, Wi-Fi, we all have the high-speed indoor network, and with the increasement of the bandwidth we are using, it has some potentials to use Wi-Fi signal and for some wireless sensing applications. For example, the person identification and tracking, and the health monitoring, as well as the gesture recognition. This wireless sensing will require no extra devices, and comparing to the camera-based methods, they are privacy friendly. And here is the motivation for the crowd counting. For example, in the application of smart buildings, when we know the exact number of how many people are inside that building, we can optimize the heating, cooling, and lighting system to give the people a better experience, as well as minimizing the energy costs. And especially in the COVID-19, in recent years, for some public environments, such as restaurants, a grocery store, or supermarkets, they usually have a crowd count limitation. So maybe they want to use some Wi-Fi signal to count the number of people and prevent from the virus spreading. So talking about the state of the art, we already have a body of works focusing on the crowd count. For example, we have a lot of paper focusing on counting mobile crowd. That means we can use the people's movements to detect how many people are there in the crowd. However, in this paper, they also consider a total different scenario. That means all the people are seated readers or audience in a classroom, library, and they are watching a lecture or reading. So they may not have body movement can be detected using the method from the counting mobile crowd. So here is the first point. And for the existing work on the breathing signal detection and machine learning methods for stationary crowd counting, they both have their limitations. First, the breathing signal detection is required all the people to stay still for quite a long time, and the only thing they are allowed to do is to breathe. And also, they require all the people to breathe with a different rate, which is also impractical. For the machine learning methods, they have some generalization problem from seat configuration in training. So how can we count a stationary crowd in a normal setting is the problem this paper wants to stress. The key observation is while the people are stationary, they will engage in small in-place body movements called fidgets. So imagine a person is sitting in the chair. They may frequently adjust his or her position, or he will cross his legs, something like that. This movement is called fidgets. The contribution of this paper is they propose that the aggregate fidgets of the crowd can carry the crucial information on the crowd count. And the problem resembles the MG infinity queuing problem. And they develop a Wi-Fi CSI measurement framework to detect the crowd count, and finally, they validate the approach with the experiments. Let's move to the mathematical model. So, first of all, we like to share some statistics that is crucial in the detection problem. First finding is a person's fidgeting process is actually a Poisson process. This figure shows if there's a person seated, when the value is 0, it means that this person is staying still, and there's no fidgets. When this value becomes 1, it means that there is a fidgeting duration is observed, and we can define the TI as the interfidget time. That is the time interval between two fidgets from one person. The gamma n is the average interfidget time for the nth person. So we can, because this is a Poisson distribution, this interfidget time can be modeled as an exponential distribution with the average gamma n. And we also know that for the fidget duration and the average fidgeting rate, they are both random variables, so they have their own distributions. When we consider multiple people in a crowd, we will observe a superposition of n Poisson process, and this process will result in a Poisson process with a summed rate. So here is the figure. We have n persons in total, and any person in fidgets will result in value 1 in the aggregate process, and the overall interfidget time is defined as in this equation, and we can see it's still a Poisson distribution, and the rate for this Poisson distribution is the sum over all the individual Poisson distributions. But the only problem is this interfidget time is not measurable because of the overlaps of the fidget durations. So how can we find some measurable parameters to infer the number of counts? We can take a close look at this aggregate process. When the value is 1, it means at least one person is in fidgeting. So it can be defined as a CFP. And when the value is 0, that means no person in that time interval is fidgeting. The CFP is the crowd fidgeting period, and the CSP is the crowd silence period. So what we can measure is actually these two parameters. And the next step is to derive the probability distribution of both the CFP and the CSP. So the author shows in the paper that this problem resembles the MG infinity queuing problem. Say the M here is arrival process. That is the exponential distribution we already mentioned. And the G here is the service time. The G here means it can be any generic distribution. And the infinity here means the number of servers. So in this problem, it resembles there are an infinity number of servers. So that means we have a client in the waiting line. And when the server are idle, it can come to the server, and after that, when the service ends, it will leave and the server becomes idle again. So The relationship between this problem with the MG infinity queen problem is showing as follows. First, the client arrival is just like the starting of fidget, and the busy period is almost the crowd fidgeting period, and the idle period is the crowd silence period. So we can use the mathematical method from this MG infinity queen problem to find the distribution of both the CFP and the CSP. The distribution is derived as follows. So we have the, it's not derived, it's directly listed here. So the CFP follows this distribution. You can see it has some underlying parameters with the total number of people, the average fidgeting rates, and it also has the CDF of fidgeting durations. And also for the distribution of CSP, it's quite similar with the distribution of the inter-fidgeting times. So it also have total number of people in their distribution equations and the average fidgeting rates. So even when we have both of the distribution of CFP and CSP, we can use MAP estimator to estimate the crowd number N. So here is the equations. We want to maximize posteriori distribution probabilities when we observe some GI and SI, which means the duration of CFP and CSP. So after that, we'll end in this equation. Inside that, we have a prior distribution of P gamma, means the distribution of the average interfidget time. And because the individual people are independent from each other, we will have the distribution of the CFP and the distribution of CSP here. So the only thing remaining is this prior distribution. We will talk about it later and first introduce the Wi-Fi processing pipeline. And any problems so far? Oh, okay. So let's move on to the Wi-Fi processing. Here is the pre-processing. We want to extract the fidget-related content from the Wi-Fi signal. So in most literature on the RF sensing, we know that the frequency and bandwidth of received Wi-Fi signal will increase when the speed of the moving person or objects increases. So the breathing signal is a slow sinusoid motion of chest. The chest displacement can be up to 5 millimeters, and the breathing rate is 0.3 hertz, with the instantaneous speed being 0.01 meters per second. As a counterpart, the fidgeting is an in-place body movement. It has 5 times larger instantaneous speed than the breathing signal, and it's for the 80% of the time. So the result of the fidgeting will be more significant than the result of the breathing signal. And we can use a high-pass filter to extract the fidgeting-related information because the speed is larger, the frequency and bandwidth will be larger. So the high-pass filter will remove the impact of the user breathing. So the first step is the stream selection. We have 60 total independent streams. That comes from 2 independent phase differences, since we have 3 antennas of the Wi-Fi transceiver, and we have 30 subcarriers. So in total, we have 60 independent streams, and we want to select 10 biggest SNR streams from this 60 candidates. The signal to noise ratio is defined in this equation. The BBR here is denotes the grazing bandwidth, that is the bandwidth of interest. So we have a signal term, which means the power falls into the bandwidth of interest, and the noise term is the power falls outside the bandwidth of interest. So we can define the SNR in this equation. And after that, we select the 10 streams with biggest SNR, and then we do PCA denoising and select the first principal component to extract the fidgeting information. For the following principal components, it composed of the noise and other irrelevant features. And we use the hypothesis test to detect the CSP and CFPs. So here is the H1. The hypothesis is there is at least one user fidgeting inside the duration, and H0 is otherwise, which means no user is fidgeting inside that duration. So they defined a threshold in the calibration period when the variance also, or in other words, the power of the filtered signal is larger than that threshold. We can indicate that there is a CFP, otherwise it is a CSP. So they compare it to the ground truth result. They let the two-person use a mobile equipped with an accelerator, and when the fidgeting occurs, using the Wi-Fi signal, we can observe the superposed fidgeting events. And at last, in the CFP and CSP detection, we can observe that this detection successfully tell the CSP and CFP. So this method can work in different kinds of scenarios. So at last, let's move to the experimental results. There are two kinds of high-level classes of activities. The first class is the audience style activities. And the second class is the reading style activities. Remember, we just mentioned the prior information of the average fidgeting time. So in these two different classes, we will have different distributions, because for the audience style activities, the people are watching a lecture or listening to some talks. It may not as that focus comparing to the reading style activities when all the users are reading. This prior information comes from the YouTube videos. The author use the YouTube videos and watch and collect the statistics inside of all the individuals inside that video. So we can see the blue line. Blue line shows the audience, the distribution of the interfidget time of an audience, and the red dash line shows this interfidget time of the readers. We can directly observe that for the readers, their interfidget time are larger comparing to that of the audience because they are more focused. For the subfigure on the right, it shows the fidgeting durations. We can see these two different classes shows little differences. That means the distribution of the fidgeting duration are quite similar, regardless which environment or scenarios these people are inside. And here is the distribution of the CFP. We know that the CFP distribution is the aggregate interfidgeting time. So when n increases, which means the people are become more and more, we can observe more likely to observe the higher duration of the fidgeting period. So here are the test environments. They conduct three non-through-wall settings, conduct several experiments on three non-through-wall settings. The first is the outdoor space, and the second is the indoor space. In these two settings, they are counting an audience, and for the third settings, that is the roof space, they are counting readers. For example, let's look at the counting result on outdoor setting, counting audience. Here is the seating configuration. The transmitter and the receiver is putting in front of the crowd. And the first setting is in total 10 users in a 442 configuration. And the second setting will have 9 users in a 5-4 configuration, and the third setting configuration consists of only 6 users. And we can observe that this subfigure shows the estimated number of people, and the dashed line shows the true number of people. There is a gap in the first few minutes because this system needs a complete CFP or CSP. So in the first few minutes, it may not measure a complete CSP or CFP. So the estimated number may be away from the true number of people. And as time goes by, it will converge to the true number of people as when the number of measurements is enough. So both in 10 people settings and 8 people settings, they both show these properties, and we can also refer to this table. We can conclude that there is a 94.74% accuracy. That means the counting error is smaller than 1. So this proposed system can work in this environment. And they also conduct some experiments in the through-wall stationary crowd countings. But I doesn't put this result here because the result is quite similar. So I just show the summary of all these experiments. With both the non-through-wall settings and through-wall settings, the probability of counting the accuracy is 0.963 in the non-through-wall settings and 0.9 in the through-wall settings. We can observe that there is a slight degradation, but the accuracy is still high, up to 0.9. And the mean square error and the mean absolute error is less than 1. At last, the correlation coefficient, which shows the correlation between the estimated value and the true value, is also high. And for the non-through-wall settings, it can be up to 0.959, and for the through-wall settings, it is 0.904. So it also shows the effectiveness of the proposed system. There are some discussions based on the experiment. The first thing is, does this interfidget times really follows an exponential distribution? So if you remember, it is assumed to be exponential distribution, but during that experiment, the author finds that the empirical PDF is very close. If we have a curve, we fit that to exponential distribution. So this question can be answered that the prior distribution is indeed an exponential distribution. And the second problem is the impact of people moving nearby and the static multipath. While we know that the multipath is static, so in the Wi-Fi signal, it is the DC component and it can be removed by the high-pass filter. So the static multipath will not have an influence in this system. But interestingly, for the moving people's impact, it is also negligible when the rate is less than the average fidgeting rate. But to our surprise, that if the moving rate of these people nearby is larger, it is still negligible. So the author put it in plan to study it in the future work. And for the characterization of the maximum number of people, so how many people, how can it be scaled to a larger crowd? The current system relies on the duration of CSP and CFPs, so the performance is expected to degrade. This is because when the number of crowd getting larger, it's more likely that the CFP will overlap with each other. So it may take a very long time to get enough measurement for both complete CSP and CFP. And it's very likely that there is no CSP at all if the number of people is quite large. So it can be a potential problem. And at last, let me conclude this paper. The crowd fidgeting behavior is actually carrying the information on crowd count, and we can use this fidgeting statistics to estimate the number of people in that crowd. They proposed a new mathematical models for the relationship between the crowd fidgeting statistic and the crowd counts. And they also proposed a Wi-Fi processing pipeline to extract the crowd fidgeting period and the crowd silent period. And last, they conduct some experimental validation. And this approach with less than one counting error is for the 96.3 when the setting is non-through wall, and 90% when the setting is through the wall for most of the time. And that's all for my presentation. Thanks for listening. Any questions?
Let me stop recording, then we can further discuss it, okay?